السلام عليكم ورحمة الله يعطيكم العافية. اليوم رح نبلش بالstudy heat conduction chapter 17. We'll cover just one or two sections from this chapter. In this chapter we'll talk about the steady conduction in plane walls just without heat generation. According to the Fourier's law of heat conduction that we introduced back in chapter 16, as you can see it's here where the conduction heat rate through a plane wall equals to minus Ka times the temperature gradient. And here we will be limited just to the spatial one dimension. So if we, for a plane wall without heat generation, then the temperature profile will be linear profile, and assuming a constant thermal conductivity, then the heat rate by conduction through the plane wall reduces to this form, Ka times delta T divided by L, where delta T is T1 minus T2. Now the equation may also be rearranged and introduce a concept of the resistance, the thermal resistance, where this is a conduction thermal resistance. So where the conduction thermal resistance, if we compare the two equations or the two forms of the Fourier's law of heat conduction through a plane wall without heat generation, then the conduction resistance or the conduction thermal resistance of the wall equals to the thickness of the wall divided by K times the cross-sectional area. Analogy between the thermal circuit and the electric circuit, where the temperature difference is analogous to the voltage potential, the heat rate is analogous to the electric current, while the thermal resistance is analogous to the electrical resistance. Similarly, this may be extended to the convection and to the radiation as well. For the convection, put this in the form that the convection heat rate equals to delta T divided by R, then that means that the convection thermal resistance equals to 1, the reciprocal of HA sub S. And again, this is how we draw the thermal circuit. Similarly, for the radiation, put it in the form delta T divided by R radiation, then the R radiation will equal to the reciprocal of H, the radiation heat transfer coefficient times the surface area, When the surrounding temperature equals to the free stream temperature, as we mentioned back in chapter 16, then the concept of combined heat transfer coefficient is introduced and present, where the combined heat transfer coefficient equals to the convection heat transfer coefficient plus the radiation heat transfer coefficient. Here, as we expect, the heat from a surface will be, if both convection and radiation are significant, then the heat will be leaving the surface by these two modes. Okay. Now this is how we draw the thermal. This is if this is a plane wall where both sides of the wall are exposed to moving fluids of different temperature and probably different even fluids. Then we will have convection here, then conduction, and then another convection, where T infinity 1 greater than T1 greater than T2 greater than T infinity 2. So this is how we plot the temperature distribution, and this is how we draw the thermal network. So here we have convection thermal resistance between T infinity 1 and T1 according to Newton's law of cooling. Then we have a conduction wall thermal resistance, while here we have another convection thermal resistance. In case we have radiation here as well, then we will have the convection and the radiation resistances are in parallel. Okay, similarly here, if we have radiation, we will have then the convection 2 plus the radiation 2 in parallel with each other. Now, same as for the electrical analogy, we will have the total or equivalent thermal resistance. Depends, here the resistances are in series, so the total resistance is simply the sum of these resistances. If we have the resistances in parallel, as we will see in a little bit with the general thermal network. So again, here delta T, how it's related, and then we introduce the concept of overall heat transfer coefficient, where the reciprocal of the total thermal resistance equals to the overall heat transfer coefficient times the A. The overall heat transfer coefficient is widely used, especially in the construction codes. So it's more common to see the overall heat transfer coefficient value to represent the different elements of a structure. Okay, let's move to the general, to multi-layer. Multi-layer, simply that will add another conduction thermal resistance as shown here. If we move to the thermal contact resistance, generally in between two solid layers, it doesn't look as smooth as we can see here. There are gaps. There are gaps that can be filled either with air or with some other fluid, and that would result in an additional resistance called the contact thermal resistance. The contact thermal resistance or the thermal contact resistance. This thermal contact resistance is inversely proportional to the contact pressure. As the contact pressure increases, the thermal contact resistance decreases. And there are values for this thermal contact resistance that are shown in table 17.1. This is shown as the contact conductance. The contact conductance is simply the reciprocal of the contact of the thermal contact resistance. So it's the inverse of the thermal contact resistance. This the contact resistance if the fluid at the interface is air, helium, hydrogen, and that results in different values for the contact conductance. The higher the contact conductance, that means the lower the thermal contact resistance. The thermal contact resistance. Okay, so that's for the thermal contact resistance. These are values for the thermal contact conductance. Again, that's the inverse of the thermal contact resistance. That depends on the two layers of material, whether they are identical metal pairs or dissimilar metal pairs, whether they are, what's the surface condition, what's the roughness, what's the temperature, what's the contact pressure. That results in different values for the thermal contact conductance. Again, the thermal contact conductance, as shown here, is simply the reciprocal of the thermal contact resistance. And notice here that this thermal contact resistance, it's actually the thermal contact resistance for unit area. As we can see, it's multiplied by meter squared. Generally, the thermal resistance is simply Celsius degrees or Kelvin degrees per watts. That's simply the thermal resistance. So this is actually, we need to add here double prime, since it's resistance for unit area. Resistance for unit area. Now, coming to the last topic of this chapter, the generalized thermal resistance, that when we have layers in parallel together with layers in series. Same principles of the electric circuits apply here. So as we can see here, the total thermal resistance between these two layers in parallel will simply be calculated according to this equation. And if we have more layers, then simply we will add here plus 1 over R3 plus 1 over R4 and so on. So same as we used to do with the electric circuits. Here we can see this is a composite wall, consists of two layers in parallel together with a layer in series. So if we draw the thermal network, we will have T1, which represents the temperature of this surface. And since we are dealing just with one-dimensional heat transfer, then the whole side is at the same temperature T1, even though there are different layers. Similarly here. So T1 and goes, then the heat rate is distributed into these two layers. So these two resistances are in parallel, and these are conduction wall thermal resistances. Then they are in series with this conduction thermal resistance at 3, and then they are in series with convection thermal resistance since there is no radiation. If there is radiation here, then the convection and the radiation will be in parallel. Okay, that's all for this chapter. Let's move to another chapter. That's the one section actually from chapter 18, and by that we will finish all the material of this course. So chapter 18 talks about the transient heat conduction. We will cover just the lumped capacitance method. In the lumped capacitance analysis, it assumes that the lumped capacitance method assumes that the temperature is just function of time. It's just function of time, and so it's uniform. It's uniform means it does not change or vary with the spatial dimension. It does not vary with the spatial dimension. Assuming this is what's the real life applications of this. If we have, let's say, a body and we immerse it in a fluid. So the fluid is of temperature T infinity, convection heat transfer coefficient H, while this solid body is of a certain mass, certain volume, uh, specific density, initial temperature. Then the heat will transfer either from the fluid to the solid body or from the solid body to the fluid. Depends which temperature is higher than the other. If Ti is higher than T infinity, then the direction of the heat transfer will be from the body to the fluid. If T infinity is greater than Ti, the initial temperature of the body, then the heat will transfer from the fluid to the solid body. So according to the energy balance, that means that the heat transfer by convection will equal to the heat stored in the body. So that's represented by this equation here. H, this is the heat rate by convection over time. So that to give us the heat by convection, not the heat rate, that equals to the heat stored in the body. That's mCp dt. Okay, the M may be represented in terms of the density and the volume, as we all know, rho V. We may introduce T minus T infinity and to replace the dt, and so dt will equal simply to d of T minus T infinity since T infinity is constant. Now rearrange the equation and integrate. We will have this form of the temperature distribution. This form of the temperature distribution. A parameter B here is called what? B is HAS divided by rho VCP, and it's the reciprocal of the time constant. So this is not actually the time constant, it's the reciprocal, the inverse of the time constant. So the time constant equals to 1 over B. The time constant equals to 1 over B. So when can we assume that the temperature is uniform? Means it does not vary. Means it does not, sorry, it seems that we were not sharing the slides. Again, let's go back. So here in chapter 8, we will just cover the lumped capacitance method. As we were saying, the lumped capacitance method, this is the solid body, and the heat transfer, as we mentioned earlier, from the fluid to the solid body or from the solid body to the fluid, depends on which temperature is higher, the T infinity or the initial temperature of the solid body. We assume that the temperature of the solid body is just function of time, so it's uniform temperature, it does not vary with the space, and we will clarify when is this applicable and valid. Depends on a certain constraint or condition. If it's met, then this capacitance method is valid. So this is the temperature distribution after integrate this this equation. The B here, as we mentioned, it's the inverse of the time constant, HAS divided by rho VCP. Pay attention here, the AS is the surface area of the solid body. The density is the density of the solid body. The V is the volume of the solid body. The Cp is the specific heat at constant pressure of the solid body. The H is the convection heat transfer coefficient of the fluid. The T infinity is the free stream temperature of the fluid. The Ti is the initial temperature of the solid body. If we are interested in finding the time, then simply we use this form of the equation by simply take the natural logarithmic of the two sides. We will return back to this equation and we can solve for the time, depends on the problem. When can we apply? Now, if we're interested in finding the heat rate, then that at any time, then that's simply HAS times the temperature at that specific time minus T infinity. If we're interested in finding the amount of heat transfer, the amount of heat, then we use this expression, MCP times T at the given time minus Ti. If we're interested in finding the maximum heat that transferred, then that occurs when the temperature reaches the T infinity. So that's MCP times T infinity minus Ti. When can we apply the lumped capacitance method? That's when a certain parameter called Biot number is non-dimensional parameter, which equals to HLC divided by K. The LC is called the characteristic length of the solid body, and it equals to the volume of the solid body divided by the surface area. If this parameter is less or equal than 0.1, then we can say that the lumped capacitance method is valid. What's the Biot number physically represent? It represents the ratio of the convection to the conduction heat rates, or it also can be seen as the ratio between the conduction to the convection resistances. So the higher the convection resistance, then the more applicable this method would be. Now we will move to now we will solve a couple of examples on chapter 17 and the one section from chapter 18. So it's actually, if we look at it, it's just two sections, 17.3 and 18.2. Those are the two sections that are required from chapters 17 and 18. So example 17.3, it talks about something that we see every day. It's a glass window with double panes that are separated by air to increase the insulation properties of the glass window. So a double pane window that is 0.8 meters high, and 1.5 meters width. That's normal to the page here. So we don't see that dimension actually. So this is the 0.8 and the 1.5 is normal to the plane. Consisting of two 4 millimeters thick layers of glass, which is of thermal conductivity 0.78 watt per meter Kelvin, separated by a 10 millimeters wide stagnant airspace, which has a thermal conductivity. Stagnant means it's not moving. That means there's no convection in there. It's just conduction. And it's of a thermal conductivity of 0.026. Determine the steady rate of heat transfer, that means Q dot, through this double pane window, and the temperature of its inner surface, for a day during which the room is maintained. This is the room, the inside is maintained at 20 Celsius degrees, while the outdoor temperature is minus 10 Celsius degrees. Obviously, that's in the winter, during a winter day. Take the convection heat transfer coefficients of the inner to be 10 watt per meter square Kelvin each one, while for the outside, it's 40 watt per meter square Kelvin. This outside convection heat transfer coefficient includes the effects of radiation. So it's kind of a combined convection thermal resistance, or combined heat transfer coefficient. So if we were asked to plot the temperature distribution, this is how it looks from the inner side due to the boundary layer. So it appears like this. and then we have this through the glass is by conduction, so it's simply linear profile. Then through the air, another linear profile, but with different slopes, since the resistances are different. And then here another linear profile for the other glass layer, and then through convection with the outside, combined effects actually, convection plus radiation. So here, to calculate the resistances, Ri equals to R convection. And then to draw the thermal network, we draw it as this. There is this convection thermal resistance from the inside, conduction thermal resistance from the first layer of glass, then conduction thermal resistance through the air, then another conduction thermal resistance through the second glass layer, then the outside convection radiation combined resistance, and then T infinity 2. So calculate Ri, that's our convection 1, R1, that's our conduction through the glass, the first layer of glass. R2 is the R air. R1 is equal to R3 since they are identical, same thermal conductivity, same thickness, and same area. The area is simply the 0.8 height times the 1.5 width. That's the area here. That's used in all these resistances since they are in series. So it equals to 1.2 meters squared. The total thermal resistance is simply the sum of these resistances since they are in series. Now the heat rate is simply the delta T, which is T infinity 1 minus T infinity 2 divided by the total thermal resistance that we calculated, and so we get the Q dot as 69.2. This Q dot is the same as the Q dot between T infinity 1 and at T1. So we are interested in finding T1. So T1, T infinity 1 minus T1, T infinity 1 minus T1 over the Ri, that equals also to Q dot, since as we know from the analogy with electric network, the heat rate here is the same as the heat rate here, is the same as heat rate here, and so on. So the Q dot equals to T infinity 1 minus T1 divided by Ri. We benefit from this fact to calculate the T1 and find it equals to 14.2 Celsius degrees. There is this example, not here, with the generalized thermal network as this. So we can see here in a general wall, we have a brick, we have plaster, okay, and there is foam, okay. So we can see the plaster here in top or bottom of the brick is in parallel with the brick. So we have three resistances here in parallel as shown here. While these three resistances in parallel are in series with the thermal resistance of the plaster from this side and with thermal resistance of the plaster from this side, as we can see here in R2 and R6, while the other resistances are in series with each other. So we can take a look at this example 17.6. Now we will move to chapter 18, look at that section 18.2 that we covered, and check an example from that section. Okay. Okay. Okay, this example 18.1. In this example, it tells us that the temperature of a gas stream is to be measured by a thermocouple. whose junction can be approximated, this is the junction, as 1 millimeter diameter sphere, as shown. The properties of the junction are given as thermal conductivity, density, specific heat at constant pressure, the convection heat transfer coefficient between the junction and the gas is 210 watt per meter square Kelvin. Determine how long, so it means the time. We need to specify the time. So we take the natural logarithmic form of the equation that we mentioned to you in the slides. Determine how long it will take for the thermocouple to read 99% of the initial temperature difference. Okay, first of all, to check the validity of the lump capacitance method, we calculate the characteristic length, and this is a hint to all of you, always with the transient heat conduction problem, which means time-dependent heat conduction problems, we always use the lump capacitance method, even if the condition was not met, since that's the only method we have learned in this course. So to calculate the characteristic length, it's the ratio between the volume of the junction to its surface area. The volume of the sphere, as we all know, that's 1/6 pi d to the power 3, while its surface area is simply pi d square, pi d square. So that gives us 1/6 of the diameter, that's 1.67 times 10 to the power minus 4. We calculate the Biot number parameter, we find it equals to 1 times 10 to the power minus 3, which is obviously less than 0.1. So the lump capacitance analysis or the lump capacitance method is applicable and valid. In order to read 99%, it's mentioned to how long it takes to reach the 99% of the initial temperature. That means that this ratio will equal to 1%. T of t minus t infinity divided by ti minus t infinity. Here it's mentioned that, what do we have? So that's the 0.01. Let's calculate the exponent b, which is the inverse of the time constant. The b equals to, after plugging in all the values which are given in the description of the example, it gives us 0.462. So if